Hello all and welcome back to this course on digital systems. So in the last lecture, we looked at the idea of a flip-flop, the latch, and the flip-flop was essentially a programmable delay element where the data could arrive at the input at any given time, but it could go out only at the sampling edge, right? For example, when the clock went high, the data could go through, and therefore the flop was able to get the input without getting into the combinational block and corrupting the previous state, right? So of course this, how often can the input get into that combinational block was determined by the frequency of the clock. Until now we looked at combinational circuits and we never spoke about the concept of a clock or a frequency. We only spoke about delays. But going forward, when we combine sequential and combinational circuits, you will see that there is a need to talk about the clock frequency, which is also going to be related to the delay of these circuits at some level, right? So now what we will do is to get in to the idea of constructing a flip-flop from the basic logic gates that we have studied in this course. So now let us look at the construction of the flop. How do I construct a flip-flop, and what are the properties of a flip-flop, right? So the idea is the following, right? So now I will consider a simple one bit case. Okay, I'm looking at D and Q. Okay, Q, right? So this is a flip-flop. Okay, and the idea is very simple. What we want, okay, is, remember, what we actually wanted, the behavior that we wanted was on the rising edge of the flop, right? This is the rising edge of the clock. We wanted the data to go through, to be sampled and then held for the remaining period, right? So if this is your clock and this is your data, right? um, I will stick to this notation even though this is just one bit, right? If this is going from state 1 to state 2, uh, obviously I want the state 2 to be sampled here, okay, and held for the rest of the period. So it does not matter if uh, my D transitions to state 3 and 4. I want state 2 to be captured here and state 4 to be captured here, right? This is all I wanted, right? And this one was going to be ignored. Okay, this is, so how do we implement this again at a gate level, right? Because we know how to deal with NAND gates, AND gates, inverters, and so on. So it's not possible to talk about this edge triggered thing directly, a concept, right? This is ultimately, if you look at it, the flop is responding to this edge. Okay, therefore this is edge triggered. So we will look at a smaller, a slightly different variant of this, and then get to the edge triggered flip flop. Okay, we will look at what is known as a latch. Okay, I'll call this a latch. I'm not going to put the triangle because if I put the triangle, it's a flop. Okay, so this is just a rectangle with a clock. That means it's a latch. Okay, uh, what is the input? So this is D and this is Q, right? And what is the behavior of this latch? The behavior of the latch is that when the clock is high, you want data to go through, but when the clock is low, you want data to not go through. That is, whatever was sampled at the falling edge, you wanted to hold it, right? So let me show you again with a timing diagram. Okay, This is D, okay, and let's assume that it goes through like this. This is state 1, state 2, and then it's going through state 3, okay. Then here it makes a transition to state 4, and then it comes to state 5. Okay, so D is now making many more transitions in that clock period. Okay, unlike the flop, we are looking at more transitions because I want to highlight the key difference. So what should the output of this latch look like if this sequence of inputs was given to this latch? Okay, let me repeat that I am using this state diagram 1 2 3 4, even though it's only a 1-bit flop. This each of these states could only be 1 or 0, by the way. Okay, so simplest thing to assume is D is actually just going 1 to 0, 0 to 1 and back, right? So state 1 is 1, state 2 is 0, state 3 is 1, 0, 1, 0. That's how it is. Okay, that's the simplest thing to assume, or vice versa. Okay, now what should happen to Q? That's the idea. Okay, so obviously here we do not know what the status is at this point, so therefore I will say unknown. Okay, now here it will take some delay, right? It won't happen immediately, so some small delay will happen and it will go to 2. Okay, this is what this sorry this will happen, right? Now unlike a flop, what we are saying is the latch is level sensitive, right? In the sense data goes through from input to output as long as the clock is high. So when the data changes from state 2 to state 3, the clock is still high and therefore this will respond to this change. So 3 will happen here. Okay, now so if you look at for the flop, right? I mean for the latch here, the latch is going to sample the data on the falling edge, on the negative edge. That is how it is supposed to be. That is how it's supposed to behave. So whatever is sampled on the negative edge, right? So I will put that in red here. Okay, so we are not worried actually about the rising edge now. We are worried only about the falling edge because that is the sampling edge. So what will happen is state 3 will simply remain all through, right? And of course when you come back to here, it will react to this change into state 5 here. Okay, so the key difference between a flop and a latch is the flop, which was edge triggered on the rising edge. Okay, I'll just put that in magenta here. Suppose this were a flop instead of a latch, then the Q would have simply sampled data state 2 and then data state 5. It would have ignored 3 and 4 in between. The latch on the other hand allows 3 to go through but ignores 4 alone. That is, when the clock is 0, no change in the input will be recognized by the output, right? That's the key idea behind a latch, and therefore this is sort of easier to conceive from a combinational circuit, and then we will construct the flop. Okay, so how do we go ahead and build this, right? So if you look at what happens here, what happens in this phase when clock equal to 1, my Q is equal to D, right? On the other hand, so let me remove this magenta clock because it's not relevant for the latch. Yeah, now on the other hand, when clock equal to 0, okay, so this is for clock equal to 1, this is clock equal to 0. When the clock is 0, what we want is the Q to be the same state as what was sampled earlier. So we want Qn plus 1, actually the at time n plus 1 to be equal to n. In some sense, we want the same state that was there previously to be held as it is. Okay, so this is the simplest thing. So if you write this in terms of a pseudo code, right, this is what you will do. If clock equal to 1, q equal to d, right, else q equal to q. That's all. We don't want it to do anything else, right? Now how do you implement this? If clock equal to 0 you want to do something, if clock equal to 1 you want to do something else, well, that is nothing but a multiplexer. Okay, so the simplest implementation of a latch, right, is to implement it with a multiplexer like this. Okay, the select signal is controlled by clock. If select equal to 0, this is 1. Okay, if select equal to 0, we want to just hold the data as it is. If select equal to 1, if clock equal to 1, we want the D to go out to Q. Okay, this is the simplest, at a block diagram level, this is what a latch is. I'm just feeding back my Q to the input of the multiplexer, and it is supposed to hold that data. Okay, now I told you earlier that in the adder case we cannot do this. Okay, but remember, in that case I wanted the Q to actually change and then go in as a new input to that adder. That was not possible, but if the Q is supposed to be the same as what it was earlier, it is possible to do it with this feedback. Okay, so to sort of just make this more practical, right, and this comes because of the implementation details and all that of the this thing. I will draw it with inverters. Okay, and what I'm going to do now is the following, right? So what am I going to do? I'm going to say, right, so this is my clock, which is the select line. This is select equal to 0, select equal to 1, and this is my Q. Okay, so effectively this offers a very similar behavior as that of what I had drawn earlier, except that there are two inverters wherever D, for example, when you go from D to Q, you go along this path, there are two inverters. If you go along this path again to retain the data, there are two inverters. Therefore, logically it makes no difference. Okay, but I'm adding that because practically that is what you need, and to explain that you need to go to transistor level details, which is beyond the scope of this subject. Okay, so let's not worry about that. So let us analyze this structure. Okay, this is what I would call a positive latch. What is a positive latch? It means when the clock is in its positive half cycle, clock equal to 1, data will go through. When it is 0, basically it will just hold the data, right? This is a positive latch. So what is it that enables holding the data? First of all, okay, if you look at it, the path when clock equal to 0 where data is held, right, if I just look at this part of the circuit, right, assume that the clock equal to 0, that means the multiplexer is just connecting this node to this node, that's all, right, and it has disconnected the D part, clock equal to 1 part of the circuit, that's all. So therefore I can redraw this by simply having two inverters like this. Okay, so this back to back inverter, which is, when you feed it back like this, what happens is, if this is logic 0, this is logic 1, then obviously this is also logic 1, and the output, so let me call this inverter I1, I2, right? So this is I0, I1 and I2. So output of inverter I1 is 1, which is the input to I2, and the output of I2 is 0. So this is the consistent logic. Likewise, I could also have 1, 0, 0. So these two are perfectly acceptable stable states of this feedback inverter. If somehow you can write a 1 and then switch off the clock, it will store a 1. It will just hold the 1 for you. If you can write a 0 and then turn off the clock, it will just hold the 0 for you, right? In this manner, right? So therefore, this is the fundamental idea with which data can be held in the previous state, right? And this is something we have never seen till now. Okay, I have never in the combinational block, we have never fed anything back as an input, right? And note, by the way, that when I said this whole when I said in the adder case, why can't I feed it back, right, as the sum to directly to the input A? Well, because I wanted the sum to actually be different from what A was. But now I am talking about holding the same value. Look at this. These two basically are the same, right? And therefore we are just going to hold the same value always, using that, using the feedback, and therefore there's not going to be any conflict or any race condition that we have to worry about. Okay, so now what I can do is I can take this particular latch and build what is the flop. Okay, so the latch, as I said, is a, this is a positive latch. I could also have a negative latch. Okay, the idea of a negative latch is to simply take this. Okay, I can also have what is known as a negative latch. What is a negative latch? Very simple, simply reverse the polarity, right? Either you make this as 1, this as 0, okay, or alternately, you don't worry about that, you keep the polarity the same here and invert the clock. I give clock equal to clock bar. That means when clock bar is equal to 0, it will hold the data. That is, when clock equal to 1, it will hold the data. When clock equal to 0, it will just allow the data to go through, right? These are two equivalent representations. I will just leave the multiplexer input, that the same. I will just say I'm going to feed clock bar instead of clock, and that is what will give me a negative latch. Okay.